In this video, we will be discussing optimal consumption bundles and how coupons can affect a consumer's decision-making process. So with this problem, we're given a number of consumers often choose between what two different goods to buy and how many units of each good they should buy given their budget. The manager of a store wants to take advantage and produce an optimal bundle. Given the following estimates on an average consumer, what is the average consumer's optimal consumption bundle? And we're given I equals 60, so our income. Q of X equals 25, which is the maximum amount of good X a consumer could buy with given their income. Q of Y equals 36, so the maximum quantity of Y that could be bought with the income of 60. And the utility function of U equals 2 log QX plus 3 log QY. So first off, we want to look at the relationship given by the marginal rate of substitution, or MRS, which states marginal utility of X over marginal utility of Y equals price of X over the price of Y. But what exactly is marginal utility of X and Y? Well, the marginal utility of X is just the derivative of the utility function with respect to X. And the same thing for the marginal utility of Y. It's just the derivative of the utility function with respect to Y. As of right now, we do not know our prices or the marginal utility for each variable, but we can find those via a number of processes. So starting with the price of X, we can put the income over quantity of X, and that'll give us our price. So if we have 60 over 25, that will give us a price of $2.40. And we can do the same thing for find the price of Y. So income over Q of Y equals 60 over 36, and that equals $1.67. Next, we want to find the marginal utility of X, which is just the derivative of the utility function with respect to QX. So since the utility function is a log function, we can take the derivative with respect to QX of 2 log QX plus 3 log QY. And we can treat these logs as base E. So we can rewrite this as the derivative with respect to QX of 2 ln QX plus 3 ln QY. And if we were to take the derivative with respect to QX, our marginal utility of X equals to 2 over QX. We can do the same thing for marginal utility of Y. So we take the derivative of the utility function with respect to QY, and that will give us 3 over QY. So now that we know both our marginal utilities and both our prices, we can plug them back into our marginal rate of substitution, which again was marginal utility of X over marginal utility of Y equals the price of X over the price of Y. And we know that the marginal utility of X was 2 over Q of X, and then marginal utility of Y was 3 over QY, and that was equal to $2.40 for price of X over $1.67 for price of Y. So simplifying things out, for the left side, what we can do is we can have 2 over q of x times the reciprocal of the bottom, because we're dividing fractions of qy over 3, and we can set that equal to 1.44. So that then gives us 2qy over 3qx equals 1.44. And if we were to multiply both sides by 3qx, that would then give us 2qy equals 4.32qx. And then if we divide both sides by 2, we're left with qy equals 2.16qx. And this is our opportunity cost, or what we give up in order to gain one more. So in order to gain one more of good y, we would have to give up 2.16 of good x. Now that we have our opportunity cost, we can attempt to solve for our optimal consumption bundle. So using another formula for income, so income equals the price of x times the quantity of x plus price of y times the quantity of y. And this will tell us our budget. So how much of good x we can get and how much of good y we can get optimally. And we know that income was 60. We know that the price of x was 2.4 times q of x, which we don't know yet. And our price of y was 1.67, and we do not know what qy is. But we can substitute our opportunity cost in there. So what we're left with is 60 equals 2.4 qx plus 1.67 times 2.16 qx. And if I were to multiply the 1.67 times the 2.16, that would give us 3.61 qx, and the rest stays the same. And now I can combine like terms, so I'm left with 60 equals 6.01 qx. And then if I divide both sides by that 6.01, I am left with a q of x equals 9.98. Now that I know what my q of x is, I can now find my q of y, and I can do that by simply plugging it into the opportunity cost. So I have qy equals 2.16 times 9.98, and then my q of y will be 21.56. And now I have found my optimal consumption bundle. Let's say that this store issues out a coupon that gives $15 off if you spend $5 on good X. And we want to know what our new budget line is going to look like. So, what we want to do is draw the graph. So we'll have is a standard graph with q of y and q of x as our axes. And our budget function looks something like this, with our maximums for qy and qx being 36 and 25 respectively. And we want to figure out how the coupon affects our graph. So first off, we want to figure out where the shift occurs. So we want to figure out how much good X do we have to buy in order to get the coupon to work. So if we spend $5 of good X and the price is $2.04, we would have to buy 2.08 of good X. We also want to figure out what our new maximum amount of good X we can buy is. So we have our income of 60 plus the $15 off that the coupon gives us all over the price of 2.4, and that'll give us 31.25. So this is our new maximum amount of GoodX we can buy. If we go back to the graph, we can now make note of where the shift occurs and how it changes our graph. So we know the shift occurs at quantity of X of 2.08, and we know our new maximum is 31.25. So we can change our budget line to look like this. And thus, our new budget line is represented by the highlighted portion. If we were to draw the utility functions as well, we would have the original utility function that we use to help find our optimal consumption bundle, and then we would have a new utility function that is reached because of the coupon. By issuing coupons, the store is able to increase consumer utility as well as sell more of a particular good. That will conclude this video on optimal consumption bundles.